Okay, so the next part that we have here, we made it to functions. We came from basically the Cartesian. We started from the Cartesian product of two sets, or basically two non-empty sets. And from there we made it to the concept of a relation, and the next logical thing after a relation is a function. And if you have understood basically the concept over here, we said that the Cartesian product of two sets was basically, for example, suppose that you had, you had two sets, for example, 1, 2, 3, and let's say that you had another set, for example, 4 and 5. The Cartesian product of these two sets was A times B, which was a set containing these ordered pairs of, for example, 1, 4, 1, 5, and we had 2, 4, for example, and then we had 2, 5, 3, 4, for example, and 3, 5. This is the Cartesian set of these two sets. Now suppose that you basically define a relation based on A times B according to some rule. Basically, and that rule is basically always some relationship between your x's and y's. So you would call this x and you would call this y, for example, and then you define some relationship between x and y. For example, you say that x is 2 times y, or y is 2 times x, or something like that. And based on that rule, you will get a subset of this set. You can call it, for example, R for relation. And then you would get, for example, 1, 4, and for example 1, 5, and then 2, 4, and so on and so forth. For example, let's say that based on this relation that you have defined, you get these 3 ordered pairs in a set, and you call it R. Now if the relation that, and of course based on the same, according to the same procedure, you can of course create as many relations as you want, depending on the number of the ordered pairs in this set. For example, if you have 1, 2, 3, 4, 5, 6 ordered pairs over here, the total possible number of subsets of this set would be, for example, 2 raised to the power 6, which is 64. So you can have 64 different subsets of this set. So each of those 64 subsets would practically be a relation. Now a function is basically a specific kind of relation that you can basically define on the Cartesian product of two sets. Meaning that if you in the process of defining a relation, if you define that relation in a specific way, in a very specific way, that relation, you can call it a function. And of course that when I say is a specific way, what I mean is that you define your relation based on some definition, and that definition is basically the definition of a function in general. And that's basically what we want to do in the rest of this video. So what that means is that now if you go over here, let's read through this part, and there are a couple of definitions and there are a couple of examples, and it's not really that much of it, I mean, it's not really a lot of material, just a little bit of material, because we have already done the main concepts, we have already done them. So it says that in this section we study a special type of relations called function. It is one of the most important concepts in mathematics. We can visualize a function as a rule which produces new elements out of some given elements. There are many terms such as map or mapping used to denote a function. Now, as a definition number 5, we say that the relation f from a set A to a set B, the relation from a set A to a set B is said to be a function, so you hopefully now understand all of the terms and everything that is used in this definition. Otherwise, you need to go back and pay more attention to what you don't understand here. So it says that the relation from a set A to a set B is said to be a function if every element of set A, if every element of set A has one and only one image in set B, has one and only one image in set B. So you need to pay close attention to these words. It says that if a relation from a set A to a set B is said to be a function, so for example, yes, let's say that you have these two sets over here, call it set A and set B, and then you have basically these elements over here and these elements over here, and if you want to define a relation, you can say that, for example, this is mapped, this element is mapped to this element, this element is mapped to this one to this one, and this one to this one. So you can call it the relation R. Now, you can call this, for example, A1, A2, A3, and A4, and you can call this B1, B2, B3, and B4. And so these ordered sets would be, or which is practically the relation R, would be basically A1, B1, A1, B1, and then you have A2, B2, and then you have A3, B3, and then you have A4, B4. That is basically the set R, which is a relation related to the Cartesian product of these two sets. Now what this definition is saying is that a relation from a set A to a set B is said to be a function. This relation, you can call it a function if every element of set A, has one and only one image in set B, meaning that this element A1 cannot have more than one image in set B, meaning that, for example, the image of A1 right now is B1. Now if I connect A1 to, for example, B2 as well, now A1 has two images in set B, so then R could not be called a function. But if A1 has only one image in B, A2 has only one image in B, A3 has only one image in B, and A4 has only one image in B, then you can call this relation, you can call it a function. It's basically that simple. And of course, you see, if, for example, if A1 had two images in B, it would be this basically this situation over here. You would have your x-axis over here, your y-axis over here, and then, for example, let's say that A1 is, for example, this point over here. And if A1 is mapped to B1 and also to B2, then what happens, let's say that this is B1 and this is, for example, B2. Then A1 is mapped to B1 and also mapped to B2. Now when you take a look at your function, when you reach the point A1, you don't know whether the value of the function at this point is B1 or B2. There is no way to tell, because at this exact point there are two outputs related to this input, and so this cannot be called a function. And we have talked about this before as well. We talked about the vertical line test. If I draw a vertical line over here, you see that the line basically intersects with the graph of the function at this input, intersects with the graph of the function at two different points, which means that this is not a function. But on the other hand, let's say that you have this situation over here. For example, the line, let's say that you have the line f of x is equal to x. This is a function. If I do the vertical line test, you see that this line, if I slide it from negative infinity all the way up to positive infinity through the domain of this function, from here all the way up to here, you see at any point that the line is intersecting with the graph of the function only at one point. Anywhere you try this, you will get only one point. So then this is called a function. And as you can see here, this set over here is nothing but, this whole set over here is nothing but this set over here. And this set over here is nothing but this set over here. So when every element of A is mapped to only one element of B, then you will get some situation like this, where, for example, this element over here, A1, is mapped to only one element in the range. So this is your domain, this is your range. So that's basically very simply that definition. So we say that a relation from a set A to a set B is said to be a function if every element of set A has one and only one image in set B. Or in other words, the function f is a relation from a non-empty set A to a non-empty set B such that the domain of f is A and no two distinct ordered pairs in f have the same first element. So it's again the same story basically. So then we can say, in other words, the function f is a relation from a a function f is a relation from a non-empty set, from a non-empty set, from non-empty set A to a non-empty set B, such that the domain of f is A, such that the domain of f is A, and no two distinct ordered pairs in F, and no two distinct pairs in F have the same first element. So it's basically another way of saying the same thing, but in basically probably in a better way or in another way. So if f is a function from a to b and a comma b belongs to f, then f of a is equal to b. So then this is about the image. So then we can say that if f is a function from a to b, if f is a function from a to b and a comma b belongs to f, meaning that this ordered pair is an ordered pair in basically in f or a part of f, then technically we say that f of a is equal to b, where b is the image of a under f, where b is the image of a under f, and where b is the image of a under f, and a is called the pre-image of b under f, and a is called the pre-image of b under f. And the notation that we used for a function from a to b, a function basically f from a to b, is basically this notation, f from a to b. This is the notation that we used. Now let's go back to a couple of examples that we'd had before and see if they were basically, so far we have been talking about different relations. So for example, we had an example number 7. If I go back to the example number 7, so example number 7 is, for example, this example over here. So the situation was basically like this. I had a set A which was basically 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, and 6, and you wanted to define a relation from A to A by we wanted to define a relation from A to A by basically this rule, which was basically R is equal to X comma Y, such that Y is equal to X plus 1. Y is equal to X plus 1. So this was the situation, and we wanted to, we were supposed to basically depict this relation and write down the domain, the codomain, and the range. And if you do so, then basically you will get, what you would get is, basically if we did solve this problem, and then your R would be basically something like some set like this. For example, 1 comma 2, and then you have 2 comma 3, and then you have 3 comma 4, 3 comma 4, and then you have 4 comma 5, and then you have 5 comma 6. And if I use the arrow diagram in order to show this relation, what I would get is 1, 2, 3, 4, 5, and 6. That would be basically A. Again, goes to A, 1, 2, 3, 4, 5, and 6. And this is again A, and then you have basically 1 to 2, then 2 to 3, 3 to 4, for example, 4 to 5, and 5 to 6. And so the domain of this function would be, the domain would be 1, 2, 3, 4, 5, and not 6, of course, because it's not mapped to anything. The range is basically 2, 3, 4, 5, and 6, and not 1, because it's not mapped to. And the codomain is basically 1, 2, 3, 4, 5, and 6, which is the set A itself. Now you can see that, for example, in this example, this relation R that we have defined over here, this relation R is not a function because I don't want to give you wrong information. So looking at the previous examples, for example, we can see that in the relation in example 7, which is this example, that the relation in example 7 is not a function, because the element 6 has no image. This has no image. This has no image, and therefore, since there is one element over here that has no image, this R is not a function. Not a function. And of course, in the definition we said that basically a relation from a set A we said that the relation from a set A to a set B is said to be a function if every element of set A has one and only one image in set B. Every element. And over here you can see that not every element has been mapped to some other element in the other set. And so what that means is that, so this is not a function. Or if you take a look at example number 8, what we can see is that the example number 8 was basically something like this. Now I don't want to give you all the details, but it was basically that the arrow notation was basically 9 was 4 and 25 over here, and these elements were mapped to 5, 3, 2, 1, 5, 3, 2, 1, negative 2, negative 3, and negative 5. So 9 was mapped to 3 and negative 3, 4 was mapped to 2 and negative 2, and 25 was mapped to 5 and negative 5. That was the situation over there. This was the set P and this was the set Q. And so, for example, this was example number 8. Now this is a relation R basically over here. It says that in example number 8, basically R is not a function because the elements in the domain are connected to more than one image. This is connected to 2 images, this is connected to 2 images, and this is connected to 2 images. So then you can say over here that R is not a function. R is not a function. And similarly, we had another example number 9. So example number 9 was basically something like this. So we had basically 2 sets over here. We had the set A over here, which was 1, 2. We had the set 1, 2, and we had the set 3, 4, and we had the set 3, 4, and we wanted to basically find the number of relations from A to B. So the number of relations from A to B were, or basically A times B was the Cartesian product of A and B was basically this set over here, 1, 3, 1, 4, 1, 4, 1, 2, 3, 2, 3, and 2, 4. 2, 4. Now, if I take one of the subsets of the Cartesian product of A and B as the product of A and B itself, meaning that every set is the subset of itself, meaning that one of the subsets of this set would be, for example, some set R, for example, having all of these elements, 1, 3, 1, 4, 2, 3, 2, 4, and that would be, for example, R. And again over here you can see that 1 has been mapped to 3 and also 1 has been mapped to 4. 2 has been mapped to 3 and also 2 has been mapped to 4. So this is not a function. This is not a function. So that is basically that. Now let's do a couple of examples here. So suppose that, for example, suppose that you have N as the set of, suppose that you have N as the set of, I don't know where my mouse is. Suppose that you have N as the set of natural numbers. N as the set of natural numbers. And the relation R be defined on N such that we define a relation on N, such that R is equal to basically all x comma y, such that y is equal to 2x, and x and y belong to the set of n. So then basically you have this relation defined on n. So what that means is that you want to find the domain, the range, and the codomain of R. You want to find the domain, the codomain, and range of R. So basically the set of natural numbers is basically 1, 2, 3, 4, and so on and so forth, all the way up to infinity. This is the set of natural numbers. And this relation goes from n to n. So you have 1, 2, 3, 4, and so on and so forth again. So this is again the set of n. So the Cartesian product of n and n, which is n times n, would be basically all of these elements basically connected together, meaning that 1, 1, 1, 2, 1, 3, 1, 4, all the way up to 1, infinity, 2, 1, 2, 2, 2, 3, 2, 4, all the way up to 2, infinity, and all the way up to infinity, infinity. Now, from all of these ordered pairs, what you want to choose is all the pairs that have basically this condition where y is 2x, meaning that, for example, when your x is equal to 1, your y is equal to 2. When your x is equal to 2, your y is equal to 4. When your x is equal to 3, your y is equal to 6, and so on and so forth. This is going to be the set R. Now, as you can see, the domain of this function is going to be 1, 2, 3, 4, all the way up to infinity. So your domain is basically the set of natural numbers. Your domain is the set of natural numbers. Your range is going to be basically all the basically 2, 4, 6, 8, all the even natural numbers. So you can say all even natural numbers. All even natural numbers. And the codomain of R is going to be basically again in the set of natural numbers. And of course you can see that R is a function because every element in your domain, or every element in this first set over here, has been mapped to some element in the second set. So this is going to be a function, and there are no two distinct ordered pairs that have the same first element. So as a solution, we have the domain of R is the set of natural numbers n, the codomain is also n, and the range is the set of even natural numbers. And since every natural number n has one and only one image, has one and only one image, this relation is a function. Okay, so that is that. Another example that we have is, and again, if you want to have a way to basically, here you have y is equal to 2x. The graph of this function would be basically this line over here. Would be this line over here, going through the origin and going through this point 1, 2. But of course your domain is basically, this is the x-axis and this is the y-axis. Your domain is, of course, considering that the domain is the set of natural numbers, and the range is and the codomain, which is this axis over here, is again the set of natural numbers, meaning that you don't take these as a set of real numbers. Otherwise, for example, 0.5 would be right over here, this point over here. If this was a real number line, then for example then the number 0.5 would also be here and would be a part of the domain of the function, which is not the case here. Your domain is basically only natural numbers. Or as another example, so suppose that, for example, you have the relation over here, for example, r is equal to, for example, 2, 1, 2, 1, you have 3, 1, and you have 4, 2, 4, 2. So this would be some 2, 3, and 4. This would be some situation like this, 2, 3, 4. And you have 1 and 2 in the other set over here. And you can see that 2 is mapped to 1. 3 is mapped to 1. And 4 is mapped to 2. So in this situation, as you can see, every member of this first set over here is mapped to some element in the codomain, and it doesn't really matter if basically 2 and 3 have the same images, as long as basically here the reason that has been given is that since 2, 3, and 4 are the elements of the domain, 2, 3, and 4 are the elements of domain of R, having their unique images. Meaning that Okay, so the reason that has been given in the book in the case of this example is actually not incorrect, but it's a little bit confusing. It says that since 2, 3, and 4, since 2, 3, and 4 are the elements of domain of R, are the elements of domain of R, having their unique images, having their unique images, this relation R is a function. This relation R is a function. Okay. Now this could be a little bit confusing, meaning that there is no good way to understand this sentence. But you can always use the definition that we used. You can always use the second part of the definition that we used, and that basically would always work for you. Meaning that in the second definition that we used for these functions, we said that basically in other words, a function f is a relation from a non-empty set A to a non-empty set B, such that the domain of f is A. So this is a non-empty set A, this is a non-empty set B, and a function is a relation from a non-empty set A to a non-empty set B, and such that the domain of f, the domain of the relation f, is basically A, and no two distinct ordered pairs in F have the same first element. So the distinct pairs of the distinct pairs in F in this case are 2, 1, 3, 1, and 4, 2. So it says that no two distinct elements of distinct ordered pairs in F have the same first element. So now here you see you have two distinct elements in F, right? Call it F, for example. And they do not have the same first elements. They have basically the second elements in the case of these two distinct pairs are of course the same. But the first elements are not the same. And so you can call this a function. But not the other way around, meaning that for example if you had this situation over here, for example 2, 3, 4, and 1 and 2, and let's say that this is, for example, this set is A and this set over here is B, and then let's say that, for example, 2 goes to 1 and also goes to 2. And then, for example, let's suppose that there is some other element over here, for example, 1, 2, 3, and 4, for example, and let's say that 3 goes to 3 and 4 goes to 4. This is not important here. Important here, what I want to show is that basically 2 has two images in the codomain. So this is not a function. But these two different pre-images have the same image, and that can be considered as a function. There is no problem with that. This is a function. Now, and what is important here is that, for example, let's say that in this case, we had this situation over here. Let's say that you had, for example, this situation over here. For example, you had 1, 2, 3, 4, and 5, and something like this. And 5, as you can see, is not mapped to anything. 2 is mapped to 1, 3 is mapped to 1, 4 is mapped to 2. 5 is not mapped to anything. Then this is not a function. Because every element in set A has to be mapped to something. Otherwise, this cannot be a function. So, that's basically that. And part 2 of this question is r is equal to 2 comma 2, r is equal to 2 comma 2, 2 comma 4, you have 3 comma 3, you have 4 comma 4, you have 4 comma 4. So you see that these two distinct ordered pairs have the same first element. So this is not a function. This is not a function. Or we have another relation over here. For example, we have this relation over here. So that is 1 comma 2. We have 2 comma 3. We have 3 comma 4. We have 4 comma 5. We have 5 comma 6. We have 6 comma 7. We have 6 comma 7. So since basically you see 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. But this is a function and there is no problem with this. There is really, you see that 1, 2, 3, 4, 4, 5, and 6. And it doesn't really matter whether basically these numbers in the second numbers have been repeated or not. That would be a function whether or not the second numbers are repeated or not. So again, the reason is since every element has one and only one image, this relation is a function. Now we have another definition here. Which is a function which has either R or one of its subsets as its range is called a real valued function. And further, if its domain is also either R or a subset of R, it is called a real function. So there are basically two things over here, a real function and a real valued function. So a real valued function is basically a function which has either R or one of its subsets as its range. Is a function that has either R or one of its subsets as its range. Is a real valued function. And you know basically what range is. And if its domain is also and if its domain is also either R or a subset of R, either R or a subset of R, or a subset of R, it is called a real function. It is called a real function. Now, of course, there is no way to know why this definition is necessary at all, because basically R or one of its subsets, I don't know what is meant by that. So we could probably take a look at this definition. Let me see. Okay, so about these two definitions, basically there is first of all the definition of a real function, and there is also the definition of a real valued function. So these two. So what they're saying here is that a real valued function is a function that has either R or one of its subsets as its range, meaning that the function is a function that is basically goes from, for example, from some x to basically R. Now this is the range of your function, and if the range of your function is the set of real numbers or some subset of that, which is, of course, the definition is not clear at all. You don't know, because, for example, this set over here 2, 3, this set is also a subset of real numbers. Or this subset could really be any set, really, so there is no way to understand what's meant here. But anyway, what they've said here is that if f is a function that has some domain, and the range of that function is the set of real numbers or some subset of that, then that function is called a real valued function. A real valued function. A real valued function. Okay. Now, if the domain of this function is either R or some subset of R, meaning that, for example, if in addition to the range being R, if the domain is also R, meaning that you can write f goes from R to R, then this function is called a real function. And that's basically that. So but the problem is that since they're saying that it could be the set R or basically a subset of R, then the definition is not very clear. Now, but that doesn't really matter, really. It doesn't, I mean, as far as we are concerned, it doesn't really, it's not really that important. Now, as an example, it says that let n be the set of natural numbers. So, for example, you have the set of natural numbers. N is the set of natural numbers. Let n be the set of natural numbers. Define a real valued function. Define a real valued function. Real valued function. Define a real valued function. A real valued function f from n to n by f of x is equal to 2x plus 1. So we said that basically a real valued function was a function whose range is basically the set of real numbers or some subset of that. Now here basically we have the set of natural numbers here, and of course the set of natural numbers is a subset of the set of real numbers. So based on the definition, everything is okay. And so the rule of the function is f of x is equal to 2x plus 1. So now the way that they have, using this definition, completed the table given below. So the table is basically something like this. The table is something like this. Here you have x and y. Here you have x and y, and then you have these values, like for example 1, you have 2, you have 3, you have 4, you have 5, you have 6, and you have 7. And so for example over here f of 1 is equal to 2x plus 1. So 2 times 1 is equal to 2, 2 plus 1 is equal to 3. F of 2, let me erase these parts so that we have some space to work with. So suppose that f of 2, if x is equal to 2, then f of 2 is equal to 2 times 2, for example, 2 times 2 plus 1, which is equal to 4 plus 1 is equal to 5. So that is equal to 5. That is equal to 5. Now number 3, if x is equal to 3, then f of 3, for example, would be 2 times 3 is equal to 6 plus 1 is equal to 7. If x is equal to 4, then for example f of 4 is equal to 8 plus 1 is equal to 9. If x is equal to 5, for example, then f of 5 is equal to 2 times 1 is equal to 10 plus 1 is equal to 11. F of 6, for example, would be 2 times 6, 12 plus 1 is equal to 13. F of 7, for example, would be basically 2 times 7, 14 plus 1 is equal to 15, and so on and so forth. So that is basically now this function, and this function, the domain of this function is the set of natural numbers. The range of this function is set of natural numbers. And well, you can call it a real valued function because I think, well, I would suppose that I would say that the definition is a real valued function, as opposed to, for example, imaginary numbers or something like that. Other than that, there is no possibility, because if the range of the function is the set of real numbers or some subset of that, then that would be all the numbers that we have, and except for those numbers, then we have only the imaginary numbers. So I suppose then that's basically that. Now the next part that we have here is basically called is basically some functions and their graphs, which I don't think we need to talk about here. You have already there is some material over here, but these are really not required anymore, at least here. Now if we need them, then we will get back to these in the next parts. We can now go back to calculus and then talk about limits and derivatives. So I'll see you in the next video. Thank you.